All right, let's look at an application involving a trig derivative. So this is a problem, similar to something that you should have done in pre-calc 2, only it didn't deal with a rate of change. It dealt with just finding a missing side, and here we're going to be looking for a rate of change. And so we've got a 50-foot pole casts a shadow S. Find the rate of change at which the shadow is changing with respect to the angle of elevation of the sun when the angle is 45 degrees. So that means find ds d theta. ds, since s is the shadow and theta is the angle, ds d theta is the rate of change of the shadow with respect to the angle. And so anytime you're doing a derivative in calculus, when you're dealing with a rate of change, you should never substitute values into the original equation unless it is something that is constant throughout the problem. So in this problem, the 50-foot pole, this is 50 feet. So we know that the 50, that's constant. We know that there is a shadow, and we don't know how long it is, but the angle of elevation to the sun is theta. That would be the angle of elevation is the angle from horizontal up to the sun. So this is our S. So we want to find ds d theta, so we first need to come up with a relationship between theta, S, and this 50. And we know this is, we're going to assume that's a right angle. So the relationship between 50s and theta is tangent. So I know that the tangent of theta, tangent is opposite over adjacent, so that's going to equal 50 over s. Now I want to solve for s, so I definitely want to get s out of the denominator. So I'm going to multiply both sides by s. So I get s tan theta is equal to 50. Canceling the s's. If I divide both sides by tan, I get s equals 50 divided by tan theta. But it's much easier to look at that as s equals 50 cotan theta. And the reason why I say it's much easier is that if you leave it as 50 over tan theta, you have to use the quotient rule. And if I write it as 50 cotan theta, I don't. I can just use the constant. I can use a constant multiple times a derivative, and I know the derivative for cotan. So coming down here, I'm going to get ds d theta is equal to 50 times the derivative of cotan, which we said the derivative of cotan was the negative cosecant squared of theta. Again, I'm going to write my derivative in a way that might be a little bit easier to evaluate. I'll leave the negative in the numerator with the 50. The reciprocal of cosecant is sine, so I'm going to get 50 over sine theta squared. Now, sine squared theta and sine theta squared are the same thing, and since I know I have to evaluate using an angle, it's much easier to leave it as sine theta. So now, even though a trig derivative is only defined for radians, if I'm just plugging an angle in, sine theta, I can plug in 45 degrees or pi over 4. I'm going to get the same answer. I know that I'm going to get 50 over the square root of 2 over 2 squared, because the sine of 45 degrees or the sine of pi over 4 is the square root of 2 over 2. The square root of 2 over 2 squared is equal to 1/2, and when I divide negative 50 by half, I'm going to get negative 100, but you have to think of the units on this. It's going to be the rate of change of the angle, of the shadow with respect to the angle. The shadow is in feet, and the derivative is only defined for radians, so this is in feet per radian, that negative 100. Now the problem asks us to leave our answer in feet per degree, so I need to convert my answer. So I've got the negative 100 feet per radians, and I need to multiply by pi over 180, because this is radians and this would be degrees, and so the radians will cancel and I would be left with feet per degree. We can do this on our calculator. So if we do this on our calculator, we take the 100 times the pi over 180. We get negative 1.76 approximately feet per degree. So what's happening is, this makes sense, as the degrees increase, the feet or the shadow is going to get shorter. That's a negative relationship. So for every 1 degree increase in the angle of elevation, so as the sun is rising, then you're going to get a decrease in 1.76 feet in your shadow, which makes sense, because as the sun goes up, the shadow gets shorter. As the sun goes down, your shadow gets a lot longer. And so there's your answer right there.